Now, back to our book. By the way, all the figures that I'm showing here are all extracted from this book that I mentioned earlier, so Building a Large Language Model from Scratch by Sebastian Rashka. I have asked him for permission to use his book for this webinar, and he was kind enough to give me the permission to use it. He was very happy that we're using his book, by the way. So that's quite cool. You can buy the book if you want, right? But I'm just insisting that all the figures are coming from this book. Yeah. Now, let's dive a bit into the transformer architecture. So this is a simplified view of the original transformer architecture. So the transformer is basically made of two components: the encoder on the left side and the decoder on the right side. The encoder, what does it do? It produces a vector representation of a text. So if you give the encoder a text like this is an example, right? First of all, you need to preprocess the text, convert it to tokens, convert it to vector, and then the encoder will produce a vector representation of this text. Then this vector representation can then be fed to the decoder, because, for example, you want to translate this as an example into German, and at the end you get das ist ein Beispiel. So this is an example in German. So you need to do translation. You need both sides. You need an encoder and a decoder, but you can use encoder only or decoder only, depending on what you want. So BERT, for example, is an encoder only, right? It will just create embeddings, so vectors that you can use for classification purpose, that you can use for sentiment analysis, that you can use for document classification. For example, you can use you can throw all your articles or books into a classifier, and it will classify according to some categories that you have predefined. Now, the pre-trained models like for machine translation, summarization, fiction writing, code recommendation, and so on and so forth, they are using the decoder component only. Now, as I said, right, we have two key components. Yeah, one is the encoder, one is the decoder. Right, so the encoder receives inputs, and how it's trained is quite important. The encoder receives inputs where words are randomly masked. Right, so an encoder is not trained to generate text. It's trained to understand the text in a sense, right? To understand the whole sentence. That's why it's trained differently than a decoder only. The decoder is trained using text and is trying to predict the next word in a text, in a sentence. So the way they are trained is different. Yeah. But one of the main components of a transformer is the attention mechanism. Now, the attention mechanism is not shown here, but it's really about understanding the words in the context and the context. But this is something we will look into chapter 3 of the book. So not today, because we don't have enough time, but we will look in the next episode of this. Yeah. There was a question on few shot, zero shot earlier. So GPT like large language models, so the models that have been trained, that are decoders only models, they can do multiple things. They can do text completion. So for example, saying breakfast is the, and then ask the model to generate the rest of the sentence. You can also give a zero shot, so you give an instruction to the model to do a task, right? So you say, okay, translate English to German, and it will just translate breakfast into Frühstück. And you have few shots. So few shots is basically you give the large language model a few examples of what you are expecting the model to do. Like, for example, in this case, it will correct the typos in a few words, and it should be able to correct at the end the typo in the phone word, right? And what is impressive, by the way, with Gemma is that if I look at Gemma, I tried these exact same examples with Gemma, right? So, for example, I asked to translate English to French, and it says, okay, sure, here's the translation of breakfast from English to French. So in French, breakfast is petit déjeuner. Now, also I've used the same exact example with few shots learning. So I give him an example of how to correct the word goat, how to correct the word shoe, and then I ask him to check the if there's any typo in the word phone, and he was able to correct the typo in phone. Quite impressive for such a small model. And then I used also the example with breakfast. So I give just the start of a sentence, breakfast is there, and then it just completed the sentence saying breakfast is the most important meal of the day, and so on and so forth. So I think that's quite impressive, given that it's much smaller model than GPT or Llama, for example. All right. Any question here? I hope you're still with me. All right, yeah. Okay, cool. Let's continue. I see that the time flies, by the way, so I was not expecting that that it would go so fast. So we are 38 minutes into the meeting, so probably will not be able to finish everything I was planning to, but anyway, I'm going to schedule follow-up meetings. Now, just it's quite interesting to see, right, how how GPT-3 in this case was trained. And here you can see that GPT-3 was trained based on a number of data sets like Common Crawl, Web Text 2, and the number of tokens of these data sets are quite impressive. So for example, in Common Crawl, you have 400 billion tokens. And it looks like GPT-3 has been trained with 60% of training data coming from Common Crawl, and then 22% of web text, 8% of books, and so on and so forth. These are internet-based book corpuses. And the number of tokens is roughly equivalent to the number of words, or maybe a bit more. But anyway, we'll see how to tokenize later. But it's quite impressive how many tokens you need to collect and you need to feed into large language models to be able to train. By the way, the GPT-3 has not been trained on the whole of the data set, but on a sample of 300 billion tokens. So if you add up 410 plus all the rest, you get 500 and something. But in fact, GPT-3 has been trained only on a subset of the whole data set. Okay, now let's look at the GPT models, right? Or decoder-only models. So a large language model using the decoder component only is simply trained to predict the next word. That's all. And this is quite impressive. If you look at the previous examples here, right? I was able to explain to a large model what to do and how to, with a few examples, how to correct some typos in English words. But in fact, this model has been trained only on predicting the next word, right? So how we go from there to interpretation of tasks and be able to execute tasks in a large language model, that's also a quite interesting topic. But anyway, let's look at how models are trained. Yeah. So like I said earlier, the GPT architecture employs only the decoder portion, so the right side of the transformer, the full transformer architecture. By the way, GPT-3 was introduced in 2020, which is already quite a long, long time ago, right? It's 4 years ago, right? Because, but these models, like the newer models like Meta, Llama, or Gemma, or others, are still based on the same concept, still using the same decoder architecture, still using the same attention mechanism, maybe with a few tweaks here and there, how they use algorithms, or which algorithms they are using for different things. We'll see that later, but the architecture is still based on the transformer architecture published in 2018. So how is it trained, right? The first iteration, you input this into the decoder. The decoder will predict the second word in the sentence, and then you will say this is. Then this is fed back into the decoder, and we ask the decoder to predict the next word, and then it will output this is, and then it will go into, and so on and so forth. So this is how the decoder works. It's predicting the next word. Now, we'll go into more detail how to build a large language model. So we are almost over with all the basic understanding of large language models, and we'll go more into how to build a large language model. So the book, by the way, from Sebastian is made of 3 main stages. The first stage is about learning how to build the LM. So we will learn about the fundamental preprocessing steps and how to code the attention mechanism, and that's going to be quite interesting. Not today, but next time we'll look into how to code the attention mechanism. And the attention mechanism is really the heart of how large language models are working. Then, in the second stage, we will learn how to code and pre-train a GPT-like large language model. And then in the third stage, we will learn how we could fine-tune the large language model. So these are the 3 main stages that we will talk about. So in summary, what did we discuss today? LLMs have transformed the field of natural language processing. That's quite clear. We have seen that modern large language models are pre-trained on a very large corpus of text, unlabeled text. So this is really unsupervised learning because we don't need to label the data. We just feed text into the model, and the model will learn to predict the next word. Then, depending on what we do, we can fine-tune models on smaller. We can have, for example, just a few hundred of examples that we can use to fine-tune a model. That's possible. Large language models are based on transformer architecture. We've seen a very high-level overview of transformer architecture. And the key idea is the attention mechanism. So this is something we'll look into next time, or maybe in part 3 of this presentation. What else? Yeah, for example, once a large language model is pre-trained, the resulting foundation model can be fine-tuned. We said that, right? So this is a summary of what we've seen so far. Any remark or question? No? All right, then. Don't hesitate. So the first step, as we've seen in the previous slide, is really to prepare the data, right? So prepare the data to be able to process text. And one very important concept is the concept of word embeddings. Probably you heard about this word embeddings. What is a word embedding? Neural networks cannot work with text directly, obviously, right? Because text is categorical, right? You have a certain number of characters, and these characters can be labeled, for example, from 1 to 26, or a number of characters for each language and so on. But this is not compatible with mathematical operations. So we need to represent the words as vectors, as continuous valued vectors.
Recording in progress.
And this is what we call, this concept of converting data into vector format is called embedding, right? So you can embed multiple things, right? Because depending, you can have vectors of multiple dimensions, and given you can have a vector of 100, 200 dimension, you can represent a lot of things because you are representing something, a text or an audio or a video with continuous valued vectors. So you can represent unlimited number of things without having any duplicates. Here's an example of embedding technique. And one of the earlier and most popular examples was word2vec. So word2vec was a neural network architecture that was trained to generate word embeddings by predicting the context of a word. So the main idea was that words that appear in similar contexts tend to have similar meanings. So these words were closed in the vector space. So you can see that, for example, vector embeddings of different types of birds were quite close to each other in these two dimensions. Obviously, you have more dimensions in embeddings, but in 2 dimensions, they would be close enough, right? And also, country capitals would be close. So, and the idea of this embeddings concept is, first of all, to have a vector representation of words or tokens or sentences, and you can then use these vectors to calculate similarities between concepts or words, but that's a different topic. But before you can do word embedding, you need to tokenize text. Tokenized text means that you have, for example, 4 words in a sentence, and then you give an ID to every word. So if you have a vocabulary with 10,000 of words, then or even more, for example, the word this would have the ID 40134, and the word is would have 2052, and so on and so forth. So this is, each word will have an ID. Let me show you quickly here. In fact, okay, I shared with you the GitHub repository of the book. That's quite interesting because you can play around with it. So if we look at the first part, right, Sebastian is using a text called the verdict. It's just a text that you can now download from the internet, and it has 20,400 characters. Now, before training a large language model, you need to tokenize. So you need to split the text into words, like I said earlier. So for example, you do it here in Python, then you get hello, a space, world, a space, and so on and so forth. So, but probably we don't want to split only on white spaces, but also commas, because if you have world and dot here and hello, comma, probably that's not going to help much, right, in the training later on. So we'll split on commas as well, on dots, and so on and so forth. So here you have the result, right? We have a split, hello, comma, null, space, and so on, right? And then you can remove the spaces, and at the end you have a nice preprocessed text that looks like this. And now you have all the tokens you need to start training the model. But before you can train, as I said earlier, you need to convert the tokens into ideas. And these ideas, the number of ideas depends on the length of the vocabulary you have in your text. If you have a very long text, you may have more words, or if you have a shorter text, like here, we have 1,159 words, okay? So what we do, we convert all these words in ideas, and then at the end, you have, for each of the words, you have an ID, right? So for question mark, you might have the ID 10. For Claude, you have 27, and so on and so forth. Okay. So then you can develop a class in Python to tokenize your text, and that's it. And then you get, at the end of the day, you get, for this sentence, you get this sequence of ideas. So this is really the first step in the training, right? So going back, so the code is quite simple, right? You go from tokenized text to ideas. Now the next step is, okay, we just did that. So you have a sentence, you have a vocabulary, right, with all the words from your text and even more. And these words, they have an ID, then you convert your text into a sequence of IDs. Quite simple. Yes, that's right. I mean, simplified, yes, of course, this one is simplified, yes. You can go much deeper than that, because now we're just tokenizing at the word level. But in fact, most of the large language models are trained with byte pairs. So not complete words, but portions of words. But we can go into that a bit later. Okay. So now let's assume we want to prepare the embeddings, like I said earlier, but before we prepare the embeddings, we need to prepare the input target pairs, right? Because we said that the decoder, sorry, is trained to predict the next word, right? But then when we are training, we need also to know what the next word should be to be able to calculate the loss of the model. So basically, we need a pair of input and target. So we need a pair of text samples with the input, which would be learn, and the target would be learned to. And then input would be learn to predict, and then the target would be learn to predict one. So every time you add one word, and then the model will try to predict the next word. I mean, you can say one word, or you can try to predict more than one word, right? So this is the principle for data sampling. So you take samples from your input text, and you define a sliding window because you want to predict the next word, or the next two words, or the next four words, for example, right? So how does it look like if you represent that in a matrix, right? So we have, or in PyTorch, so we have the inputs, that could be the tensor X, and the tensor X would be the first four words of this sample text. And then what we expect from the decoder model is that it will output the next word after these four words. So after in the heart of, it should then predict the word the, right? So the target pair is simply the text shifted by one. So you can see the heart of the. So this is the input in the heart of, and then we shift by one so that during the training, we train and we try to predict the next word with this the. Now we could try to predict 4 words. In this case, it would need to predict the out of the, right? So, and so on and so forth. So it's a very important concept to understand, because then it explains how large language models are trained using data sampling from text, so random samples, and then with sliding window. So basically trying to predict next words or next tokens. And that's an example I was just giving. So you can predict one word at a time, so a stride of 1, or you can predict 4. And then you have no overlaps between the input and the tokens. All right. If you look at I don't want to go through the code now, not enough time, but you can look by yourself. It's quite interesting. Now, there was a question on simplified. Yes. So what I was showing was really word tokenization. So splitting only by words, but there's something called byte pair encoding. So byte pair is about breaking down words into the problem is that you may have words that you've never seen before. Now, if you break the words into smaller sub-word units, there might be a better chance that you don't have unknown words in the training process. And, and then the tokenizer is used here by GPT-2 is a byte pair tokenizer. So basically it breaks down, here you can see it as an example, it breaks down this sentence, hello, do you like tea? And then it adds a new token, by the way. It breaks down this, this sentence into multiple tokens. So I think there are more tokens than words. I haven't counted really, but that's the idea, basically, that you break down words into smaller pieces even. Right? So I think I'll schedule a follow-up meeting with, I'm almost over, I'm not fully over, but it's been 1 hour, so I don't want to bore you with more.